Hello everyone, and welcome to this session. A topic that I'm very passionate about is Docker and databases. Just a little bit about myself first. My name is Andrew Pruski. I am a field solutions architect for a company called Pure Storage. Before that, I was a database administrator for my sins for around 15 years, mainly specializing in SQL Server. We've got some Postgres in there, MySQL, smattering of other ones in there as well. I am a Microsoft Data Platform MVP, Docker Captain, VMware vExpert, generally just all-round database nerd, basically. As I said, my Twitter handle, although I'm not really on Twitter that much anymore, ever since, well, you know what happened to Twitter. At DBA, but there's my Gmail account there as well, dbafromthecold@gmail.com. So if you have any questions after today, or you just want to reach out and talk about stuff, please feel free to do so. I am always willing to talk about this stuff. Blogs there as well, loads of articles about running databases in containers. If you want to check that out, you are more than welcome. And then my GitHub account. All the slides and the code for the demos that we'll be doing today, because this is a very demo-heavy session. It's pretty much all demos. Are available on my GitHub, and I will post an exact link to that repo at the end of the session. But on to today's session. Today, we are going to be talking about Docker and databases, but mainly the different options that we have for persisting databases in Docker. How can we use them? How can we persist one database from one container to another? So let's start with why databases in Docker. Why would we want to run a persistent storage technology such as databases in something that's basically ephemeral by nature? Well, let me tell you a story. It's a few years ago now. I was working for a company in Dublin, and I should mention I'm from Dublin, Ireland, but I'm originally from Swansea in Wales, and that's why my accent is a bit here, there, and everywhere. Got out of Britain just before Brexit kicked in. So working for a company, and we have a QA department, and that QA department has a whole bunch of VMs that they do their testing on. Each one had an instance of SQL Server installed. And every month, they went through a refresh process. They blew all these VMs away, rebuilt them, reinstalling SQL, pulling the databases in from a centralized server, restoring them, pumping data in, and then they're good to go. This process took around 45 to 60 minutes per VM. It's quite an involved process. So we decided to blow that all away, get rid of those instances of SQL, and have them contact a remote host and spin up a container running SQL Server from a known Docker image that we refreshed on a regular basis. And we had different images depending on which branch they were working on at the time. We timed this, and the longest it took to get a fully instance of SQL Server up and running, fully configured with their data all ready to go was 2 minutes, down from 45 to 60 minutes. We worked it out that it saved around a month's worth of dev time a year. Very powerful when it comes to your CI/CD pipeline testing, things like that. So that's why databases in Docker, really. We get all the benefits that containers give us. Ease of deployment, spinning up from a known configuration, testing new versions. We can spin up a new version of whatever relational database or NoSQL database we're working on. Do any testing. If there's a problem, we can easily roll back as well. Because, and this is the key thing, I've got a colleague out in the States called Anthony Nocentino, and he says in one of his sessions talking about containers that nobody cares about Postgres, MySQL, Oracle, SQL Server, yada, yada, yada. Nobody really cares about the compute, do we? Really? We don't. We just care about the data. And we care about that data being able to be accessed by something. Now, when I tell this to DBAs, they're like, really don't like that. Mainly because us as DBAs, we've been used to stroking our compute, whispering sweet nothings to it, patching it, looking after it. You know, our VMs are physical machines. We spend a lot of time maintaining them. But containers change that. It's the pets versus cattle analogy. VMs and physical servers are pets. Containers are cattle. We don't fix a container. If something goes wrong with that container, I'm sorry, but blow it away, spin up a new one. We don't care about the compute. We only care about the data. So what options do we have for persisting our data? Well, there's three main options that we have, really. We have bind mounts, mounting from the host. named volumes, creating a volume within Docker and mounting them into a container. And then we have something called data volume containers. Now, really, all these are doing is creating an anonymous volume in the background. But what we do is we spin up a container, we create a container with a load of volumes in it, and then we grab those volumes and shove them into another container in the background. It's a bit of an edge case, a bit of a weird one, but we'll go through all of them. The first one being, let's talk about the architecture. Sorry, I always forget about this slide. Very simple. We have our host where we run our containers. And then we have our file system here. Now, we have tempfs mounts, which we're not going to discuss here because it's not persistent. But we have our file system, and then within our file system, we have that Docker area. Bind mounts reference a location that we specify somewhere on the host, whereas name volumes are just a location within the Docker area that Docker manages. We don't interact with ourselves. We do it all through Docker. All name volumes are created, managed, maintained by Docker itself. So the first one, bind mounts. As I said, this is mounted directories from the host. We use the absolute path, no shortcuts here. And the cool thing about these is they can be created on demand if Docker is running root on your system, which, okay, can cause issues. We basically take a directory on the host, mount it into our container, and then we can come along, access, come along, access, come along, access. I don't like bind mounts, really, if I'm honest. Mainly because you're putting a dependency on the container on the host. Containers, the whole point of containers is that they contain all the necessary binaries and libraries required for a piece of software to run in the same manner, regardless of its environment. If we start putting external dependencies there, when someone pulls that image down and runs it on another host, and that location on the host isn't there, we can run into errors. It also things like permissions errors. Anyone here ever had an overactive sysadmin come along and start cleaning up file systems on servers? Start blowing away files. Like, what is all this database stuff here? Gone. Then you're going to kill your container. Where these come into effect are where I see people wanting to put very large databases into containers for the access. I work for a storage company. We do some cool things with snapshots. You can snap a volume, clone it, snap it, clone it, snap it, clone it, and then have a container come along and access it. I've got a customer who's wanted to do a 320 terabyte database and put it into Kubernetes. Okay, yes, you can do that, but probably not the best idea in the world. But that's a use case for bind mounts. What we should really be doing is using something called name volumes. These are volumes managed, maintained by Docker. This isn't rocket science. It's a volume with a name. We basically just say, Docker, create this name volume, and then attach it into a container. No dependency on the host. And the key thing here is the life cycle is external and independent to any container referencing it. Compute and data are separate. Containers can come along, access, blow it away when we need to, spin up a new one, new versions. Anyone here ever tried to roll back have we got any SQL people here? SQL Server people? Wow, okay. Okay, rolling back a patch for SQL on Windows is an involved process. It's a bit of a pain. But with containers, we can just spin up a new one, add the lower version, have it access the data. Really powerful stuff. And of course, if you're working locally, which we'll be doing here with Docker Desktop on Windows through WSL, or on Mac, these things have a higher performance than bind mounts by a country mile. So if you're doing any testing, and you're going down through the operating system to your bind mount, you're going to get less performance than if you're using a name volume. Last one, and this is the last slide I promised, and we'll get into the demos. These are data volume containers. We create a container with a volume. It's not in the running state. It can be, but it doesn't have to be. We just create the container. The volumes are then created by Docker in the background as anonymous volumes, and then we can create other containers referencing those volumes and pull them across. I appreciate this is a bit of an edge case. It's not always used that often. But when it is used, it's when people start creating containers with lots of volumes. Say 15, 20 volumes. You want to grab all of them at once and push them into another container. This is when this becomes really useful. So, demo time. Said that was the last slide. Here we go. Can everyone see this at the back? We all good? Yes? Cool. Okay. So I'm on my Docker, I'm on my system here. And what I'm going to do is, we'll do bind mounts first. Oh, it's going to make me type in a demo. Every time. There we go. Okay. Right, let's create a directory on the host. Just home, a Pruski, Postgres local. No containers are running. But I have my Postgres image, 432 megabytes, which for a container image is fairly big until you start looking at the SQL Server images, which are about 1.5 gig. When Microsoft were looking at the Windows container images, they were 10 to 12 gig, absolutely gigantic. Thankfully, though, Microsoft no longer do a Windows version of SQL Server, it's all Linux-based. Okay, so let's run a container. Docker container run it in the background, -d, detach, demonize, however you want to call it. Give it a name. Publish. Now, I'm using some weird ports here just to make sure I don't conflict with anything already running on my system. I'm just picking a port out of thin air and mapping it to 5432, the port that Postgres listens on. Set an environment variable, Postgres password, and then mapping home, a Pruski, Postgres local to varlib PostgreSQL data, default location for my Postgres cluster. And then go Postgres latest. Now I know friends don't let friends use the latest tag. But for this purpose of the demos, it's absolutely fine. 3, 2, 1, good. Container is running. Excellent stuff. Let's have a look at that container and we'll have a look at the mounts. So we've got type bind source, my bind mount on the host, my location on my host, destination, mode, blank for this, read write, true, great, propagation, are private. It's just something to say any of the mounts within that mount won't get propagated into the container and vice versa. Okay, so we have our container. I'm going to set environment variable so I can connect. Check the version, 16.4 Postgres, great. And let's create a database. Now with Postgres, you can use an environment variable when you spin the container up to create a database, but I'm doing it verbose here so we can see each of the steps. Okay, database is there, at the bottom there, test database, woohoo! We have our database. And within the bind mount, we have all of our database files. And in that base location will be all the files for our databases within our Postgres cluster. So let's not mess around. Let's get rid of that container. Gone. But, there we go, gone. Docker container run, Postgres 2, publish, environment variable. And now we're using the mount syntax. We have two options when it comes to working with volumes in Docker containers. We can use the mount flag or the volume flag. They pretty much do exactly the same thing. The only difference is the mount flag, as you can see here, is a lot more verbose. You get more options with it. But volume will accomplish exactly the same thing. Mount is generally used when you want to use custom drivers and things like that. But for this purposes, I'd use volume generally. And there we go. Boom. Test database is there. So nice and simple, by referencing a location on our host, we can create a database, blow away our container, and when we're ready to come back, spin up a new one, reference the same place, our data has been persisted. However, overactive sysadmin going, why are all these database files on my server here? This is a security risk, get rid of those immediately. And of course, eventually, our container will error out because at some point it'll go, hang on a minute, I haven't got any files. And we'll go, at some point, it will die, I swear. But it's one of those demos that seems to take a different amount of time every single time I do it. But anyway, let's have a look. Last time, doesn't want to die. There we go, there we go. And because if we look at the logs, could not open postmanage.pid, there's no files there, it's decided to crash. So that's one of the reasons I don't like bind mounts. You can clean up stuff on the system, throws out your containers. It could also be a security risk. Permissions can throw issues as well. Weirdly, Postgres runs as user ID 999 within the container. Doesn't run as root, which is a good thing. But for some reason, 999 maps to a system process on WSL, so it has root access to my entire system. Yay. OK, so let's do a bit of a cleanup. And we'll jump into another demo. This one, name volumes. So clear. This time we're going to do exactly the same thing. No containers are running. I'm going to create a name volume. Boom. Docker volume create Postgres data. There we go. Using the default driver, local, running on Docker desktop. Volume name Postgres data. So let's run a container. Docker container run, Postgres 3. Publish some ports, password, and now we're mapping the volume. We just referenced the name volume to that location. Now, again, we don't have to explicitly create this volume. If it doesn't exist, Docker will create it for us in the background. I just like doing things step by step when I'm doing these demos so we don't start popping up name volumes here, there, and everywhere going, where did that come from? 3, 2, 1, we're up. Container is running. And if we have a look now and we inspect that container, type, this time volume, name. I don't know why I keep looking at the screen. I can see it down here. Source, destination, our name volume, destination, where we mapped it to, driver local, mode is Z. This is an SE Linux label, which isn't obviously applicable here. It just defaults to that. Z basically means this volume can be shared between multiple containers, and we'll have a look at that in a demo coming up. And then propagation, read, write, true, all good. Set the environment variable, and then, okay, we're going to run through. We can connect into Postgres, create a database, this time test database 2, and there it is. Wonderful stuff. How are we doing for time? Loads of time. Oop. So let's get rid of that container and confirm it's not running. But we have our volume there. Still all managed within Docker. This is obviously within the Docker system, file system on the host, but we don't access it directly. We do everything through Docker. You don't want to go in there and start messing around with things like permissions and stuff. You will end up having a very bad time. But anyway, we've got our volume, so we can run another container. And this time, I'm using the mount syntax. Mount, type of volume, source, my name volume, destination, and my driver local. All it does is accomplish exactly the same thing as the volume flag. It's just more verbose. Docker do recommend using this, but honestly, dash dash volume 99 times out of 100 is good enough when you're working with this stuff. And there's our database there. Bang. Nice and simple. Create a volume, drop a container over it, do some work. When we're done, blow it away, bring a new container in, maybe at a higher version, lower version, testing new features, things like that. Really, really simple. Okay. Next one. Data volume containers. Let's get rid of that. So, no containers are running, no volumes. And what I'm going to do here is create a container. I'm not running it, but I'm mounting a type of volume to a destination within my container and then specifying a volume. Now, I could create a name volume here if I wanted to. Don't have to. I'm going to create an anonymous volume and let Docker manage everything in the background. I'm not going to touch the volumes at all with this. 3, 2, 1. Container is up and running. Oops. Container is created. Sorry. There we go. Let's clear that out. No containers running whatsoever on my system. All I've done is created a container. And in the background, what Docker has done is create an anonymous volume. This awful alphanumeric assignment here. So what I can do now is do exactly what we did before. Go ahead and start Docker container run, giving it a name, publishing some ports again, environment value, and then I'm saying volumes from my data volume container. So this is where this edge case, I admit, comes into play, where we have a lot of volumes when we take from one container and push them into the other. We don't have to explicitly map each volume going out. So when you have a container with lots of volumes, it's nice and simple to push this in. 3, 2, 1. making sure that there, we've got our version, creating our database, and there it is on our host. So create the container, got our volume, mapped it into another container, spun it up, and created a database, all supported by that anonymous volume and the background. If I now blow away my container, no container's running, but I still have my data volume container. Now, technically, I could blow that away as well, because it's like the volume's lifecycle is independent of that data volume container. However, I don't really want to have to reference that volume explicitly. It'd be an absolute pain. Okay, I can copy and paste, but really, no, don't want to do that. What I want to do is grab it and do exactly the same thing as before, volumes from the data store. Okay. There's our database. So that is pretty much the three methods of persisting data from one container to another. We have our bind mounts, mounted from the host. Use cases, wanting to mount very large databases into a container, or we just have files that we don't want to copy into a container's writable layer, we just want to mount them in. Name volumes, probably the recommended way to go. Create the volume, let Docker manage everything internally, and then mount those to each container as you're working. And then the real edge case here, which is data volume containers. Creating your container with a load of volumes underneath it, mounting those using the -- volumes from flag into another container, doing your work without having to explicitly reference any volumes whatsoever. Okay, how have we got? 15 minutes, I think? 10 minutes, okay. This has all been very noddy stuff, I do appreciate, but we're starting from the ground up, because we don't just create databases, blow containers away, remap, and then do some more work. Just look at it, basically. We actually do some stuff. We pump data in, we test features, we confirm maybe query executions are the same from one to another, stuff like that. We actually do some stuff. One of the really cool things about containers is the ability to, well, test high availability features, for example. Learn new skills very, very simply. Who here? No, it's the wrong question. Back in the day, to test stuff like this, if I wanted to test, say, replication from one instance of Postgres to another, I'd be going off, creating a virtual machine, installing Postgres, setting it up, configuring it there, then building my second instance, installing it, configuring it, and then talking between the two. Containers, by use of volumes, blow all that away. We can do this really, really quickly, get this up and running and have a look at it, test different settings, different configs as we go. And we'll do that now. Let's have a look at testing high availability for Postgres in containers. So the first thing I'm going to do is create a custom bridge network. Custom bridge networks in Docker have a little bit more advantages over the default bridge network in the fact that containers on a custom bridge network can reference each other by name, not just IP address. They can take advantage of Docker's internal DNS server. So that's why I'm spinning these up here, because I want my containers to be able to talk to each other. Let's run a container on that network with a name volume. And I'm not going to create these explicitly this time. I'm just going to say Docker container run, publish some ports, and I'm going to use the default one this time. On my network, I'm going to create two named volumes. Postgres data, supporting where my cluster is going to live, and Postgres base is where I'm going to back this cluster up to. Set a password, and I'm going to use the environment variable this time to create a database within Postgres. I'm going to call it test database 5. Give it a name, Postgres 8, from the Postgres latest image. Oop, hello, there we go. Okay. So now I have my volumes, nice and created. I know I'm being a little bit explicit here with setting this environment variable each time, but it's basically just in case Visual Studio Code crashes on me and I have to run through this all again, setting up from scratch. Database is there. And now what I'm going to do is I'm going to update a config file to allow containers to talk to each other on the IP range for the Docker containers on this host, which is 172.18.1. 0.124. So using Docker exec as the Postgres user, dropping that in. Going to create a user for replication with the password testing1122. And then open up a replication slot and confirm. Cool. So now what we're going to do, we've got our first instance already configured and ready to go, sorry. We're going to take a base backup of Postgres. We're going to back up this Postgres cluster to a location, and we're going to run the secondary instance from that location. We're going to use this name volume to share between the two containers. So we don't have to back it up somewhere, copy it, push it in. We can just use this to share between the two containers. So I'm going to take this base backup. And fingers crossed that's not going to take ages. Ah, come on. There we go. And now I can run my second container. Docker container run, publish some ports. I'm going to go 5433 on the same network so they can reference each other by name. And this time, the default data location for Postgres is going to be where our base backup was taken on our shared name volume. Set the password, give a container a name, and there we go. Nice and quick. Still got my volumes. No new ones were created. We're all referencing the same one here, Postgres base in the second container. And then we have our database, because it was in, we created that first when we spun up the first container. It's in the base backup. And now I'm going to have to update that second container with information about the primary container. The key thing here is Postgres 8, the name, the port, and the user. So on that custom bridge network, they can talk to each other by name, not IP address. And then for those changes to take start, I'm going to restart both containers. Excellent stuff. Okay. Now, moment of truth, if Andrew knows what he's talking about. We're going to create a table, very noddy table with first name, last name, date of birth, email, and we're going to insert some records. We're going to insert myself and my wife's name. She was McKenna, I was Pruski. We didn't know if we wanted to take each other's names, so we decided to mash them together and become the McPruskis. No? Okay. Anyway. Cool. Okay, those are inserted, and if everything's gone to plan, if we now query the second container, do just a select star. I know friends, don't let friends do select star, but it's a demo. Boom. Successfully set up streaming replication from one container to another in, a couple of minutes, which would even be quicker if we just went all the way through by using a shared name volume between one container, take the base backup, shove it into the second container, up we go. No copying files around, nothing like that, just a couple of config edits to make, I will admit, but nice and simple. We can get this up and running. We now have a HA setup for Postgres that we can go and play with. We can start testing different config settings, tweaking it around, playing around with it without the need to spin up a virtual machine here, a virtual machine there, make sure the networking is all sorted. It's all good to go. We can do this with any HA system. We've done it with SQL Server quite a lot, with the clusterless AG settings and things like that, playing around, making sure I can get to know this technology before I go anywhere near, say, a dev environment or a staging environment, QA environment, and then into my production environments. Really, really powerful learning tool. So we've got a few minutes left. So what I'm going to do now is pray to the demo gods that this is going to work. Because, okay, fair enough, don't really want to be explicitly building out containers, mapping config files, messing around with stuff like that. I want to drop all of this into some automated system that I can just run a command, spin it up, and it will automatically bring that up for me, ready to go. And the way to do that is Docker Compose. So let's get all of this stuff into Docker Compose and we can have a look at it. So I navigate to the directory, and we'll have a look at that compose file. So first one here, if we bring this down a little bit, I'm not going to minimize it. There we go. Right, so first one, first service. Image, Postgres, container name, Postgres1, user, Postgres user within the container. Password, and we create the database. Keeping the same ports, default port 5432 to 5432 within the container. And then we have two name volumes, Postgres data, Postgres base, exactly the same as the previous demo. And then, to make those config updates, we're actually going to mount the scripts, update the HBA-conf, create the replication user, and then take the base backup into a location within the container, the Docker entry point initdb location. Basically, with Postgres, when this spins up, it'll look in that location. If there's any scripts there, it will execute them in order. And this will configure replication for us. I then have a health check. All this is doing is, in this base backup, once the base backup is created, it's going to create a ready.flag in that location. Because the second container is going to wait for the existence of that flag before spinning up, because we need the first container up, running, and configured before we spin up the second container. We're doing that via a health check here. Then we have Postgres 2. User Postgres, and then we have a command here. Now, I can't map a config script into Docker initdb location within the container, because that only gets initialized if the varlib PostgreSQL data location is empty when Postgres spins up. If it's not, initialization is skipped, and it doesn't run any scripts in that initdb location. So here I'm explicitly copying it somewhere else, and then executing it manually. And then we can see here, depends on Postgres 1, condition service healthy. At the bottom here, we then have our volumes, Postgres data, Postgres brace, our named volumes. You can also 100% use bind mounts in Docker Compose files, but please, please use named volumes. So let's go ahead and let's execute this. Let's get this working. So we check the networks on the host. We should have just the 3 default ones, bridge, host, and null. No volumes. Let's bring that up a little bit. We go. And now we can spin up our containers with Docker Compose up and then -d detach, run it in the background. 3, 2, 1. Network created, volumes are created. It's created both of our containers, but now it's spinning up that first container, and we're waiting for our health check. It should take about 11 seconds. There we go. Nice and quick. We have, hopefully, our containers up, running, and configured. So let's have a look. We've got our networks. Yep. Compose default, it takes the name of the folder that you're in. That's why it's got Compose under there. It's not because it is Docker Compose. Nope. There we go. Got our named volumes. And we have our containers. And the first one, is up and healthy because of that health check in there. Now, I know there are probably other ways of doing this. It's just a nice, easy way. Very, very simple, just to say run every 10 seconds, check for the existence of that file, mark that container as healthy, spin up the other one. And we've got, OK, if we look at the logs, database is ready to, OK, cool, accept connections. And the second one, started streaming WoW from primary. Yes, looking good. So now, just make sure we've got our database in both of them. Yes. Oh, type. And finally, BGN recovery. Yep, it's a secondary. Let's do what we did before and stick in those 2 values into the first container. If all's gone well, bang. Yay. Nice and simple, one compose file that we can have in source control, versioned, pull it down, spin it up. We have 2 instances of Postgres with replication and streaming. Nice, quick, no messing around. Spin it up. We can do our testing, play around with configs, break them, redeploy them. It doesn't matter. They're only containers. We don't fix containers. We blow them away, rebuild them. And that's just a very simple example of some of the stuff we can do with this. By sharing named volumes, bringing the data around. There's no messing around, playing with backups, copying them down to the host, pushing them into containers, things like that. None of that. By using these volumes, we can easily move data around, redeploy, rebuild. So I'm pretty much out of time, so let's go and clean up. Nice and simple. Again, with Docker Compose, containers lifecycle is completely separate from the data, unless you're doing what I'm doing here, which is using the -v flag when you say compose down, and that will wipe out your volumes for you. So you can do a nice, easy cleanup, or remove the V, spin them down, keep your volumes. When you come back to do testing, we can spin it back up. Everything is there, still fully configured, ready to go, nice and easy. And is that? Yes. Okay, so I have a whole bunch of resources for you here, all the slides and the code for all the demos that we did in this GitHub repo. The QR code will take you there as well. Please, if you have any questions, come and talk to me. I'll be here for the rest of the day. Thank you very much.
Thank you, Andrew. This was something.
Yeah, thanks. Yes. Well, he just kept on going, didn't he?
No. Yeah, I think we have just time for 2 questions.
Yes, of course.
Yeah, they are up there. So, is this Docker specific, or you can transfer it to other container engines? The flags, most likely.
The only other one I've used is. I'd have to double check, but the concepts are the same. Any sort of container engine will be basically separate the compute from the data. So yeah, flags and syntax will be different, but the concept 100% will be the same.
Makes sense. And then the other one, backup strategy. How you do this in production?
How would we do?
Another session.
Yes, a whole other session. Actually, I do a whole session on disaster recovery strategies for databases. And the general consensus here is you need to think about your RTO and your RPO, your recovery time objective and your recovery point objective. How much data can you lose in the event of a disaster, and how long will it take you to recover? And then you need to build your backup strategy from that. And you don't have really a backup strategy. Go away, Zscaler. You don't have a backup strategy, really. You have a restore strategy. If you cannot timely restore your databases, you are going to have problems. One of the big leaders in the SQL world told a story about a bank in America who took a full backup of their databases every month and then just transaction log backups for the rest of the month. Just before the end of the month, they had a corruption issue in their primary database and had to do a restore. Restored the full backup, but then had to restore thousands upon thousands of transaction log backups. Took them 3 days. It was the end of the bank. Test your production restore strategies regularly. I'm going to stop because I could go on about this all day.
Thank you very much. You can find Andrew in the hallway.
Thank you.